Hi, folks. This lecture goes with class on Tuesday, April 14th. We're going to talk about testing hypotheses about means of paired differences. We're in section 13 of the notes, 13.3 of the textbook. All right, so we now have a procedure for doing a hypothesis test about a single population mean. We can use almost the same procedure to do a hypothesis test in a matched pairs setting. So the setup here is that we're dealing with matched pairs data. And often this will be before after treatment type data. And what we're going to do in this situation is we're going to be interested in the differences between those pairs. For instance, the differences in the data before and after the treatment to see if that treatment has some interesting effect. So we're going to ask questions about the mean of those differences, which I in the textbook are going to denote by mu with a subscript of d for differences. So let's do an example together. We're interested in body temperature before and after doing some exercise. So here's some data. This is made up, but it's a good example, where we've collected from a number of people a body temperature before and after a certain amount of exercise. What I've done with that before and after data is computed a difference. I've done before minus after. So when these numbers are positive, it means the first one, the before, is bigger, and temperature has gone down after doing exercise. When these numbers are negative, it means the after temperature is higher. The thing you're subtracting is larger. So it means the body temperature has gone up as a result of this exercise. And the question we'd like to address is whether the body temperature after exercising on average is greater than the body temperature before exercising. So let's do a hypothesis test of that using what we've learned about hypothesis tests for a single population. Our hypotheses here are the following. If nothing interesting is happening, i.e. in this example, if there's no difference between before and after, then the average of these differences should be 0. Some will be positive, some will be negative, but there's no consistent pattern. On the other hand, if what we suspect to be true actually is true, then the body temperatures afterwards will be higher. And since I'm computing before minus after, that would mean we would get, on average, negative numbers for this difference. You could do this problem subtracting in the opposite order, doing after minus before. Everything would be perfectly fine, except you'd be thinking about whether those differences are positive instead of negative. And what you'll do in that example will get answers that are very, very similar to what I'm about to do, but some of them will have a different sign than what I'm doing. You can do either way, just make sure you're consistent. All right, let's think about how we would compute the t statistic here. In this case, what we want to do is take the average for all those differences, subtract that from our null hypothesis value, which in this case is 0. Under the null hypothesis, the average difference is nothing. And then divide that by our standard error. So what we're going to do is treat those differences just as a single population data. So we're going to look at the standard deviation of those differences, and we're going to divide by the square root of n, the number of people that we have in this sample. So let's carry out this calculation. So the average difference here is minus 0.422. That's the average of all these numbers over here, which I calculated earlier. We're going to subtract 0 from that. I computed earlier the standard deviation of all these difference numbers in that right-hand column and found that it was 0.692. And then we're going to divide by the square root of the sample size. And I have 9 people in this sample, like so. Okay, so if we compute that, throw that in your calculator, you should get minus 1.83, like so. Okay, for this problem, Let's say we're using alpha equal to 0.10. And to figure out whether or not to reject the null hypothesis, what we need to do is look at our t-scores for a confidence level of 0.10, a one-sided test, and for a sample size of 9 people. All right, so let's jump over to the t-score table and clear this old stuff off. So in this example, we're doing a one-tailed test because we're just looking at the chances, an alternate hypothesis, that mu sub d is greater than 0. We're not doing the not equal version. And our alpha was 0.1. So this tells us that we will be working down the first column of this table. And then as ever, we have to find the correct row. We had 9 people in this sample. Degrees of freedom is sample size minus 1. So we're going to go to the row numbered 8, like so. And we find that the key t-value is 1.4. All right. So if we come back to our example, since our t-value, or more particularly, the absolute value of our t-value, the positive version of it, is greater than 1.4. This is the t-value from the table. Well, that t-value being bigger means it's more extreme and therefore more favorable to the alternate hypothesis. So what we know is that our p-value is, pardon me, less than our alpha, which in this case was 0.10. So at this level of significance, this data is statistically significant in favor of the alternate hypothesis, namely that body temperature increases during exercise. Whoops. There we go. And since we do see an interesting difference here, we have a positive result to this test, we should report our effect size. So what we found here was that it increased by about 0.422 degrees. That was the average of our differences. Okay. All right, so it's the same procedure as a one population mean test, except that instead of looking at the raw numbers from our population, what we do is we use the differences as our raw data and compute our average and our standard deviation from those. All right.